All right, section 10.4. Now we are looking at vectors in space.
Whoa.
3D, our physical world. Okay? Now, here's the nice thing. Pretty much everything that we've learned so far with regards to vectors in 2D, in the plane, most of those calculations will extend into 3D. Okay? So I actually want to begin with just how to find the distance between 2 points in coordinate space. Okay? So here I have 2 ordered triples. Recall ordered triples, they have 3 coordinates, x, y, and now z. Okay? And you find the distance between the 2 of them the same way you would with coordinate pairs. Okay? It's essentially an extension of the Pythagorean theorem. So the distance here, I'm sorry. I got the formula up top I got to put in. Okay, so let's say we're working with point 1 with coordinates x1, y1, z1, and point 2 with coordinates x2, y2, z2. These are 2 points in space. The distance between them would be equivalent to the square root x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. Now, if we stop there, that's our distance formula for 2D, right? But now we just tack on plus z sub 2 minus z sub 1 squared. All right, so let's apply that to the 2 sets of points below. Distance here would be the square root of 4 minus negative 1, so that's really 4 plus 1 squared, plus negative 2 minus 3 squared, plus 5 minus 2 squared. Okay, so that's going to be square root of 5 squared plus negative 5 squared plus 3 squared, or the square root of 25 plus 25 plus 9, so the square root of 59. Now 59 is prime, it doesn't have any perfect square factors, but as always, if you get a radical that can be simplified, make sure you're doing that. Any questions? Okay. Next, we'll look at how to find a position vector in coordinate space. So, we've represented our vectors so far in 2 different ways. We had component form, which is still at play here. We can use component form, or we can use standard unit vectors. In 2D, we use standard unit vectors I, J, and K. Just I and J. Here in 3D, we throw in a third standard unit vector of K. Now recall what each one of those represents. I is a vector along the x-axis whose magnitude is 1. J is a vector along the y-axis whose magnitude is 1. And now K is along the z-axis. All right. Now, let's visualize a 3D vector here. All right, so try to move this around a little bit for you. Okay, so the blue vector there is our vector whose components are 2.6, 3, and then 2.6 right now. Okay. Try to move it a couple different ways for you. This one's tricky. Goodness gracious. There we go. Okay, so notice you have those three red vectors. Each one of those would be the unit vectors I, j, and k. All right, and this particular blue vector could be thought of as 2.6i plus 3j plus 2.6k. All right, so that just helps you visualize. Okay, now, if you want a position vector in coordinate space, it's the same as in the coordinate plane. Let's say I have a vector whose initial point is p sub 1 here, and whose terminal point is p sub 2. And I want the position vector that goes along with that. So recall, that's just the vector with the same magnitude and direction, just placed with the initial point at the origin, right? So this position vector v can be found with the following calculations. You can take p sub 2's x-coordinate of 4 and subtract that by p sub 1's x-coordinate. And that's going to be a scalar on the unit vector I. And then we'll just do the same thing with the y and z coordinates. So the y coordinate would be 6 subtracted by 2. That'll be the scalar on the unit vector j. And then the z coordinates 2 minus 3 on the unit vector k. So in the end, this is going to be 5i plus 4j minus k. Or you could write it in the component form, 5, 4, negative 1. You guys know the Dos Equis commercials? I don't always fill in the blank, but when I do, I don't always joke about vectors. But when I do, I, J, K. I did not come up with that on my own. I actually have a meme for it. All right, moving forward. Hey, operations on your 3D vectors, they're the same as in the coordinate plane. So addition, subtraction, scalar multiplication, dot products, magnitude. You find them the exact same way as you would for a 2D vector, okay? So let's say I am working with vectors v and w here. And I want to add them together. Okay, well, first let me give you a 3D visual of what it means to add vectors together. Now, this is not the greatest applet to maneuver either, so bear with me here. Okay, so this applet shows 4 vectors. So you've got a black vector there, a blue vector, a dark green, and a light green. All right. I'm going to add the black vector with the blue vector first, okay? So I'm going to pick the blue there, add that. So notice what this is doing is it's drawing off of the terminal point of the black vector. It's now drawing the blue vector, and then this would be the sum of those two vectors. Make sense? So it's the same thing we're doing in coordinate plane. It's that tail to tip method, right? Where you just draw out the first vector from its terminal point, draw out the second vector, and then that will lead you to the resultant vector. Okay? Now, I'm not going to have you graphically do that. Obviously, it's kind of hard to do on 2D paper when you're in 3D. We're just going to algebraically do it, okay? So vectors v and w are given here. If I want to add the two together, just add the corresponding components. So 2 added with -3 would give me a -1 as the scalar multiplying I. 4 added with -2 would give me a scalar of 2 times the unit vector j. And then -5 added with 3, that's going to give me -2 as a scalar multiplying k. All right, next we're looking for the dot product between the two vectors. Remember, dot product results in a scalar real number. So I'm going to take the scalars on each I, so 2 and -3, they get multiplied together. And then I'll add that with the product of the scalars on j, 4 and -2. And add that to the product of the scalars on k, which is going to result in -6 plus -8 plus -15, which gives us -29 as our dot product. And recall, dot products are commutative, right? So if I ask for w dotted with v, get the same thing. Hey, wild guess, what's 3w? You know it. You know it, Roa. Perfect. Multiply each component by 3. All right, and then the magnitude of w, square root -3 squared plus -2 squared plus 3 squared. So that's going to be the square root of 9 plus 4 plus 9, which is the square root of 22. Questions on those examples? All right, cruising right along here. Finding a unit vector in the same direction as vector v and finding the angle between two vectors. You're going to do this the same way in coordinate space as you did in the coordinate plane. So let's find a unit vector in the same direction as vector v equaling 2i minus 3j minus 6k. So recall, a unit vector is just a vector with magnitude 1, right? If you want a unit vector going in the same direction as this vector v, you need to take the vector and divide out its magnitude, right? So that requires us to find magnitude of this one first. So that would be the square root of 2 squared, or 4, plus negative 3 squared, or 9, plus negative 6 squared, or 36. This is going to work out quite nicely to the square root of 49, or 7. So that means our unit vector heading in the same direction as this vector v would be 2/7 I minus 3/7 j minus 6/7 k. All right, now find the angle between vector v and vector u here. So we have a formula for that. Cosine of the angle between them will equal their dot product divided by the product of their magnitudes. You guys remember that formula? Okay, so for the two given vectors v and u here, their dot product, it would be 2 times 2, or 4, plus 5 times negative 3, or negative 15, plus negative 1 times 6, or negative 6. So 4 plus negative 15, that's negative 11. Negative 11 plus negative 6 is negative 17. Okay, then magnitude of vector v. That's going to be the square root of 4 plus 25 plus 1. So the square root of 30. Magnitude of vector u would be the square root of 4 plus 9 plus 36. That's going to be the square root of 49, or 7. All right, so the angle between these two vectors would equal inverse cosine of the dot product, negative 17, divided by the product of these magnitudes, which is 7 radical 30. And now be careful when you input into your calculator. Make sure you put that 7 radical 30 in parentheses, otherwise you won't get the right order of operations. All right, so inverse cosine negative 17 divided by my 7 radical 30. I'm getting 116.3 degrees. And recall, whenever you are expressing an angle between two vectors, it's got to be between 0 and 180, right? Which an inverse cosine function is always going to yield an angle between that, so we don't have to play around with reference angles, which is nice.